So let's continue with our little Boids. What do we have at the moment? Yes, Boids are separating from each other. We don't have this force here, but I want to, before implementing these other forces like alignment and cohesion, I want to implement a force which will drive Boids towards some kind of a target, because now they are just static. Well, not static, they are separating from each other, but they don't have a target. When they separated on the maximum distance, they kind of stops. They kind of stops. They kind of stop. I wanted to say, okay, let's say, let's introduce maybe some kind of separate or target force. Let's say each Boid has a target, vector 2 target. It's just target in space to which Boid is tending to go. Is tending go to, or to go to? I don't know. You get the idea. Velocity. Let me initialize it with 0. Target 0. Or maybe. Yeah. Target 0, and on each update step, I will set target equals to just mouse position, get mouse position. But the mouse position, it's in the screen space, but we already working in camera space. As you remember, we introduced camera, and we need to transform screen position to the world position. Get screen to world 2D. Yes, exactly what I need. Camera. Target, and we want to drive the Boid towards this target. Target separation force, let's say vector 2. Target force. Target force. Let me think. Let me draw. Friction. Let's say target. Okay. So I have a Boid in the space, and I have some kind of a target, and I want to force this Boid to move towards this target. Let's say I want to force it to move along this direction into this along this direction, like so, and this should be an arrow. Well, let's simply take the difference, vector to subtract between Boid target and Boid position. Let's call this force. Well, maybe let's do the same thing. Let's say target force is just a scale of the target vec, Boid, target score, because eventually we want to balance all the forces, and we need some kind of coefficient to scale the force. And target vec is simply target vec is simply vector 2 subtract, we want to subtract from target void target void position. This is our target vec, and we need to define target target score. Target score separation vec separation score target score, let's say 1 for now. We already tuned the separation score, now we will tune target score. Target score, we apply target score to target vec, we scale target vec, and we obtain target force. Let's maybe put it like so. This is our vectors, and this is our targets, net force, and we want to add target force. And as I said earlier, I don't want to change this code in any sense, because it's our engine, let me run the application. Do they move? For some reason they don't move towards the mouse. Net force, target force. Target force shouldn't be much larger. No, they don't move for some reason. Let me debug quickly. Printf. I want to print components of the target force. Target force x, target force y. It's 0. It's 0. Target vec. Void target. Let's print target vec. It's not 0. Okay. Yeah, it's changing. Target vec. Yeah, target force for some reason is 0. Yeah. Because I never set target force to the Boid. Target score. Sorry, target score. I meant target score. Target score. And now, did I remove this huge multiplier? Yes, I did. Yeah. And now as you can see, they are trying to separate from each other, but also they are trying to move towards the mouse. But now I don't like their separation. It's kinda it's too tight. Let's maybe decrease target score. Let's set it to, I don't know, 0.5, for example. Maybe, but maybe not. Yeah. Now, as you can see, so we want to try the balance between separation and the following the target, but also, by the way, I think we need to introduce the notion of minimum velocity, minimum speed, and the notion of maximum speed. Imagine that Boids, they are just, I don't know, birds or some creatures in the ocean, and they kinda cannot stop in one place. They always swimming or flying, So let's introduce float min speed and float max speed. Usually speed is just a float value. It's just a single scalar value. And it usually defined like the magnitude of the size of the velocity vector. Okay, let's set them. Target score, static const flow min speed is equal to, for instance, 5. Static const flow max speed is equal to 10, for example. And I want to set them. Boid min speed is equal to min speed. Boid max speed is equal to max speed. All right. And where should I cap the velocity vector? Well, actually, I do need to perform this kind of procedure in the so-called engine part, because it doesn't affect any forces, it doesn't affect any velocities. It's just restriction on velocity itself. So when I compute the velocity, let me also compute current speed. It's just the magnitude of the velocity vector. Vector 2 length Boid velocity. Let me clamp it. Speed is equal. Clamp is the function in raylib which simply does this. It's just clamping the value. Value speed Boid minimum speed Boid maximum speed. I clamped the speed, and now I want to clamp the velocity itself. So let me take the direction of the velocity. It's basically vector 2 normalize Boid velocities. So basically this is just a vector in the it matches velocity direction, but it has the unit length. And now I want to rescale it. Vector 2 scale back to the speed magnitude and assign it to the Boid velocity, like so. Let's check it. Wow, it's pretty cool. But I want maybe to increase, let me think, min speed, max speed, I don't know, let's say 20 maybe. Maybe I should increase. It's a normal process when you programming Boids or any sort of emergent behavior algorithms. You spend almost all of your time tuning the coefficients of your forces. Separation force. Let me increase target force, or maybe let me increase target force. Maybe 0.3. Yeah, for now I think it's okay for now. Let's maybe try 0.5. Let's maybe try 0.5. And what if we increase separation score? Do I like it? Maybe I don't. Maybe I don't like it. Well, now maybe I do. Now maybe I do like it. Let me try 1 here and even 3 here. Five here. Yeah, let's keep it 5 right now, for now. Okay. Let's maybe increase minimum speed, maximum speed. Yeah. Now I like it. Now I like it. And as you can see, we didn't set any kind of cohesion score. So basically the tendency of boids to group with each other. But we already have this kind of emergent behavior. As you can see, there are 2 groups, but we definitely didn't code the grouping of boids. We didn't code this behavior, but they already grouping. It's called emergent behavior. Yeah. 3 groups. Yeah, it's really cool. We just code 2 simple rules. Not 2, but 3 rules. 3 forces: damping force, separation force, and target force. And we already have some kind of interesting emergent behavior. Okay. Now let's maybe introduce the next force. And the next force, let's maybe introduce cohesion, the tendency of boids to form groups in the space. But for this we need to also, you know what, let's first improve our separation force a little bit, because I don't like the idea to separate boids over all the space. Let me try to explain. Imagine that imagine that these are all our boids in the application, all our boids, and each boid is influenced by all other boids. But I don't like this idea, because imagine that we have boid like here, many boids, a lot of boids, and the final vector, it will be just too smoothed, too averaged, because there are a lot of boids and the final separation vector is just some sort of average of all the boids. I don't like this idea. I like to introduce some kind of maybe private radius around each of the boid, and in this private radius, only in this private radius, I will compute the separation force, only in this kind of radius. Like from this boid I will separate from this boid, from this boid, from this boid, and from this boid, and only from them. How can we achieve this? Well, let's introduce some sort of a radius, separation score. Let's say here float separation, or maybe private no, let's say separation radius, and separation radius, let's say, so boids have radius 1, so these little dots on the screen basically have a diameter of 2, because radius is 1, diameter is 2. And separation radius, let's say, I don't know, maybe maybe 10 times larger than the Boid itself. I think it's fine. Maybe even we can radius times 10. Yeah, we can keep it relative to the radius itself, because if we change the Boid radius, we also change the separation radius. Separation radius. Okay. Now let's update Boids. Let me think. This is the distance. This is the distance from other Boid to our current Boid, and let's just simply say if distance is greater than Boid separation radius, let's say float influence is equal 0 by default, but if the distance is less than or equal than separation radius, so basically Boid is inside our current Boid separation circle, we can say that influence is equal to this one. Yeah. Let's check. Whoa. Where are you going, guys? Yeah, maybe I need to tune the coefficients again. Yeah, because yeah, as I said, if you don't restrict the radius of the separation, we kind of obtain the very averaged separation vector. But now the separation vector is not averaged. It's just tightly defined. It's defined by tight group around the current Boid. So let's maybe tune a little bit our scores. Let's say separation score 1 and target score also 1. No, maybe I did something wrong. Let's say just for debug purposes. Yeah. It's a mistake. Separation score influence if distance between these two Boids is less than separation radius. I say that influence. Well. Let me print the influence. Zero. It's just 0. I don't like it. If the distance. Let me print distance. Distance is alright. Let me print Boid separation radius. It's 0. I did the same mistake, I suppose. Yeah. Maybe I should just get rid of this static stuff. Separation score Boid separation radius is equal to separation radius. Yeah, let me get rid of this stuff. Mean speed, because I already did the same mistake twice and I don't like this. Target score is 1, separation score is 1, separation radius is radius times 10. Yeah, and maybe Boyd, let me put this stuff here. Radius, mass, and color. Well, I don't need color at the top. I will put it below. Position, velocity, target. Okay. This is parameters of the physical representation of the Boyd, radius and the mass. This is my radiuses, scores. This stuff I maybe should put here. Yeah, now I like the separation. Let me get rid of this stuff. Boyd is spawned true, position, velocity, target, Boyd radius is equal to 1, Boyd mass is equal to 1, Boyd mean speed is equal to like so. Separation radius, Boyd radius, separation score and target score, separation score 1, target score 1, and color ray white. Okay, now let's check influence. Okay, yeah, I like this very much. This looks perfect. Well, given the fact that we only have 3 forces. If we don't take this fact into the account, it looks pretty shitty. If you think about it. But we have only 3 forces, so it's okay for now. Okay, let me tune coefficients a little bit more. Separation score, let's say 2. $20 for contrast. Yeah. Yeah, it's cool. Well, 20 it's maybe too high. Let's say 3. Do we need to increase target score? No, we don't. I think they follow target. Maybe we should even decrease this and increase separation. Also, as you can see, the behavior is kinda, it's not particularly physical, because when they turn around, they can even accelerate, so they even increase their speed. But if you think about it, in reality, when a pack of some birds changes the direction, they cannot increase their speed, they decrease their speed. But in our situation, it looks strange. So maybe we should start not with the cohesion force, but let's maybe start with the alignment force. And alignment force, well, I don't think that alignment force would help us with this issue, but at least I don't know. Well, no, let's implement cohesion. So the cohesion, should I draw it? I don't think for now should. Yeah, maybe I should. Let's say that I have the pack, not pack actually, this are all my Boids, and I'm updating some specific Boid here. And as we discussed, we already implemented the separation radius, separation force, and whatnot. And now let's apply the same logic, but for group forming. Let's say I also have some kind of group radius, and inside this group radius I want to compute the group center of mass. The group center of mass. I don't know, for example, it's here. And I want to drive this Boid towards this center of mass as well. But first let's discuss what the center of mass even is. If I have some points in space and each point has its own mass, it could be 1, it could be 10, any sort of value. Center of mass, first of all, well, not first of all, center of mass is just the average of all these points, simple average. But we divide not by the number of points, but the total mass. And each point contributes to the final center of mass by its personal mass. I think it will be easier if we code this stuff. Separation score. Yeah, let's say I have mass. Let's introduce group radius for the beginning. Group radius. And let's say that this group radius is equal to let's say it's 3 times larger than the separation radius. Now let me go in here. So let me compute you know what? Let me compute the influence like so. So I won't have 0 influences, but if the distance is less than separation radius, I want to separate them. In this direction. I want to separate them. If the distance is less than or equal Boid group radius, I want to compute the group mass. Not vector, float group mass is equal to 0. Let me group mass plus equal other mass, but also actually group mass is starting with not with 0 but with current Boid mass, because current Boid is also influencing the general group mass, because it belongs to this group mass. Yeah, and let me introduce the cohesion vector. Cohesion vec is equal to vector 2, 0 for the beginning. Cohesion vec is cohesion with 1s or 2s. With 1s cohesion vector. Group mass, and let's say that cohesion vec is equal to vector 2 add cohesion vec but I want to scale, to add some influence, to add some weight to the to the current distance between my Boid and target Boid. Well, no, sorry. I'm saying the bullshit right now. Cohesion vec, I don't have cohesion vec right now. Well, let me think. Cohesion vector, I need to draw. Let's say I have a Boid, and I want to drive this Boid towards the center of mass. Okay, so I need basically to compute this center of mass. Yeah, I don't have a cohesion vector. I cannot compute the cohesion vector inside this loop, because to compute the cohesion vector I need the center of mass, and I don't have this. Let's say vector 2 group center. Let's set it to the vector 2 scale my position, Boid position, scaled by Boid mass. So basically I will compute group center like average value of all Boid's position in the group scaled by their mass divided by the total mass of the group. Group center, group mass. Let's compute group mass, and group center is equal to vector 2 at group center vector 2 scale position of this Boid other position scaled by other mass. Yes, group center. Now I need to normalize group center. Group center is equal to vector 2 normalize. Not normalize, no. Vector 2 scale, because, well, normalization will give us unit length vector. We actually don't want unit length vector. We want to scale the group center by the divided by the mass of the group mass. So basically it's simple average, but we averaging not along the, we taking all the object from this average with some kind of coefficient weight. In simple average we have unit weights for each object. Okay, group center. And now I can compute vector 2 I can compute cohesion vector. Okay, cohesion vec is equal to, I want to drive Boid towards the group center. So vector 2 subtract group center Boid position. This is my cohesion vector, and cohesion force cohesion force is equal to cohesion vector scaled by cohesion score, and cohesion score, let's say, is equal to 0.5 for the beginning. So let's check the results. Cohesion vec, yeah. Yes, maybe. Let's maybe try to set some kind of absurd value, like 100. It's kind of difficult to say it, frankly speaking. Let me, you know what? Let me draw the I'm not sure in this group center. Let me draw it. Let me draw the group center. Well, actually we will have many group centers because group center is specific for each Boid. But anyway, let's draw it. Draw circle V, group center with radius 1 and color red. Maybe I should, for now I should put update function. Well, how can I do this? Maybe I should put it inside the draw. You know what? Let me rename this function draw camera space. I will name this function draw camera space. Begin drawing this stuff I will put here, and drawing I will put here, and mod 2D I will put here. Draw camera space, yes. And draw camera space is just, well, let's maybe, no, let's leave it here. Draw Boids, draw camera space, and let's just put the update not here, but simply in here. And now we can draw stuff inside the update function. And later we will factor it out on the previous position, before the drawing procedure starts. Draw circle. Yeah. No, it looks correct for me. So it's just some points inside the in the middle of local groups. Yeah, as you can see now, the center is in the very center of this formed group. Let's maybe update after we draw. I don't like this kind of debugging, but for now it's okay. I want to draw the red circles on top of the white ones. Yeah. By the way, it looks very cool. It looks very cool. Let me play with this cohesion score. Let's say, let's set it to 1. Yeah, maybe. I don't know. Let's implement the next force. By the way, no, it's all right. Sorry. The next force is alignment force. Alignment force, well, all previous forces, separation, cohesion, they act in the space of the positions, of the absolute positions. But the alignment force is it's acting in a space of velocities. So we don't want to change the position of the Boid with this force. We want to change the velocity, the direction of velocity. Direction or I don't know, the direction or absolute value as well. Average heading of local flock may steer towards. I think it doesn't change. It doesn't change the absolute value. So we want to change the direction, and we want to align the direction towards the average group direction. So let's implement this stuff. So strategy is absolutely the same. Let's introduce alignment score. Let's introduce. Let's set it to alignment score. Let's set it to, for example, 1. Let's say alignment force. Well, it's basically not a force. Well, it's force, but it's acting in the space of the velocities. Let me think. And I cannot apply this force like all other forces, because I need to apply it to the velocity. So basically I don't have alignment force. Let me think. Let's first compute some kind of average direction of all the velocities in our group. So basically, if we are in the group, we compute group mass, group center, blah blah blah, but also we compute group average velocity. Group, let's say group direction. Let's say group direction is equal to vector 2 add group direction and let me think. I also want to compute, I don't know. No. Let me compute group velocity. And group velocity is just a summation of all velocities in this group, all velocities. But also, let me define it, group center, group mass, vector 2, group velocity is equal to, let's say, first of all, it's equal to my velocity, to the current Boid velocity, and after that we add all other Boids in the group to this vector, all other velocities in the group to this vector, group velocity, other velocity, yeah. And so what do we have? Let me think. Let's say I have some kind of a group, and all Boids, each Boid has some velocity. For example, here, this Boid, for example, has small velocity here, this Boid has small velocity here, and let's say I want to add them together. So this one, and this one will give me this, then I have this one, then I have this one. Yeah, it goes approximately like this. And this is a huge velocity. It may be very, very huge velocity, because I just summing up all the Boids inside the group. But I want to obtain just a direction, just a simple direction, like so, which has unit length. Direction, it's a vector, it's a unit vector. And then I want to take this direction. For example, my Boid has this velocity, yes, but I have the group direction. Let me draw it in blue. For example, this. And I want to rotate a little bit. This is group direction. And I want to rotate it towards the group direction. But on which amount? On which amount I want to rotate it? Well, maybe it's defined by the coefficient we introduced. Score. Alignment score. For example, if alignment score is 1, I always, well, I don't know, actually I don't know. You know what? We need to implement a simple rotation. So let's begin with computing this direction. Anyway, let's begin. Group velocity. Yes, I sum together all the velocities, and now I want to obtain group direction. Vector 2 normalize group direction, group velocity, vector 2 group direction, and let me compute the angle between group direction and the current Boid velocity. Float angle is equal to vector 2 angle between Boid velocity group direction. By the way, do I need to normalize somehow? Calculate angle between two vectors. So yeah, first of all, they should be in the center of coordinate space. Yeah, from origin point. Okay, I don't need to normalize them, but at least I need to be sure that these vectors are basically it's vectors, not lines. Difference between line and vector, that line has some kind of starting point in the space, or maybe not line but ray. But the vector, it's assumed to be starting from the 0, 0 point. So I have an angle, and let's say, let me just print this angle and just check values. Yeah, it's okay, it's radians, it's okay. It's alright, it looks alright. Angle. And let me call the... So it's the most difficult one, or maybe I'm tired already. Yeah, I have target value, I have target angle, and I need to rotate the blue one by this angle. By this angle. Okay, let's say Boid velocity is equal to vector 2 rotate Boid velocity angle. So I obtain the angle between the velocity and group direction, this angle, and then I rotate the velocity towards this direction. Okay, and this is our velocity. Oh, let's try to compile this stuff. Well, yes, absolutely yes. But I don't want to rotate them immediately. I want to rotate them with some kind of a factor. So let's say each Boid has a rotation speed, and let's say rotation speed is defined by score, by the alignment score. Yeah, I need to rotate by this angle, and I have some delta time. How many radians I can rotate for this delta time? So let me just, how many radians I can rotate by this delta time? Let's say I have some rotation speed, alignment score, rotation speed. I multiply this rotation speed by dt, and I obtain delta of the angle. This is my target angle. This is the angle I can rotate. Actually, I can rotate. Float angle step is equal to this stuff, angle step, and I need to apply, and I can rotate only by this angle step. So let's say if angle itself is greater than 0, I say that angle step is equal to minimum value between angle step and angle itself. So for example, if the angle is 90 degrees and angle step, for example, is 5 degrees, and if angle is positive, I say just that angle step, the step I can rotate on, is just a minimum value between angle step and angle. Angle is 90 degrees, angle step is 5 degrees, for example, I take 5 degrees. If angle is 3 degrees and angle step, and I can rotate by 5 degrees, I basically rotate only on 3 degrees. But what do you want from me? Really? Angle step is minimum. Angle step less than angle, then I take angle step. I just thought that raylib has a minimum function, but it's not a big deal. Otherwise, no, angle step is less than angle, I take the angle step, otherwise I can take the angle. Otherwise, if the angle is negative, I want to take angle step is equal to if it's negative, if angle step is greater than angle, so it basically it's less in the absolute values, because if it's negative, if angle step, you know what? If angle step is less than absolute value, let's solve this via absolute values. Angle, this one is hard, angle step, if angle step is less than target angle, if angle step is less than target angle, I just say that angle step is equal to angle less than 0 minus angle step, otherwise it's just angle step. Else, if angle step is greater or equal to angle, I say angle step is equal to, if angle step is greater, I want to take just angle. If angle step is greater, just angle. Whew. It was hard, but maybe it's not correct solution. Let me check. Angle step. So, and in this case, I basically take into the account dt. It's very important to take into the account dt, because I don't want my physics to behave in a separation from the timestamp. I want them to be tightly coupled, physics and timestamps. Angle step, then I compute angle step. If my step is less than angle, I just take, if angle is less than 0, I take negative angle step, otherwise simple positive angle step. And if angle step is greater or equal than absolute value of the angle, I simply say, okay, I can step on this angle right away. And then I rotate the velocity by the angle step. So let me, yeah, maybe I should build it and try it. Yeah. They preserve the angle, as you can see, they preserve the angle, but maybe too much. Cohesion, no. I'm already tired. Alignment score, maybe let's say 0.2. 0.2. Yeah, maybe it's okay. Let me get rid of these red circles. Also, let me bring back update function. Update function will be here. You know what? Give me a second, please. I think I finished with basic debugging, so I can return my initial structure. Yeah. Maybe I don't particularly like the initial circlish spread, but maybe it's okay because all Boids are starting from a center position, and when they are all tied together, they have very strong separation force at the beginning, and maybe it's okay. Maybe it's all right. Let's maybe increase number of Boids and tune final parameters a little bit, and also let me draw FPS and drawing and multi draw FPS. I like to put them into 1010. Yeah, as you can see, we have 600 Boids, and the complexity of the algorithm is n squared because we need to iterate over all Boids, and for all Boids, for every Boid we need to iterate over all Boids again. So complexity is n squared, but it's okay. It's okay. As you can see, I like it. Score, separation score, target score is okay, alignment is okay, cohesion maybe a little bit smaller. Wow, this is super cool. Yeah, and also as you can see, when they formed some kind of a group, common group, all boys just in one group, they cannot separate anymore. Maybe if we put the cursor here, no. Yeah, they can't separate anymore. And sometimes people add another force, sort of individuality force for each Boid, and it basically means that each Boid has some sort of probability to separate from the group. But I don't want to implement this. I want to achieve this behavior by tuning these parameters. Maybe I should increase separation force. let's maybe, yeah, I know, let's maybe decrease group radius. Let's maybe say it's equal to 2 separation radiuses. Also, I want to increase speed, minimum speed 100, 150. No, it's too much, it's too much. Well, maybe let's try to set group radius equal 1, like a separation radius. Not 1, but separation radius times 1. Well, yeah. I want this kind of clusters, And I think it's alright now. Ah, they merge together. Will they separate at some point? Will they separate? No, they... How can they separate? I don't have any separation force. I mean separation not in local sense, but in global group sense. So, yeah. What if I increase this one? Will it work? Maybe it will. But maybe it won't. Yeah, it's alright. It's alright. It's alright. Yeah. Yeah, you can tune these parameters by yourself. You can introduce new forces. So it's very simple from the idea perspective. You basically want to factor out your main engine part, which takes force, compute the acceleration, compute the velocity step, update the velocity, clamp the velocity by the maximum and minimum speed, and then finally you update the final position by taking the velocity, computing the position step, and updating the position. This is your engine. This is physics engine, and how you compute your forces is absolutely up to you. It's absolutely up to you. You can add any random force here. You can play with these forces whatever you like. You can add a lot of forces. Yes. Okay, I suppose that's it. I will create repository and commit code and attach the link in the description of the video. Bye.